So maybe a very quick example of quantifier-free types over fields. Of one element, that kind of quantifier-free type is one of two types. It's either algebraic, it means this A is algebraic over a prime field, and then it's given by its minimal polynomial. So basically, over a prime subfield of K, let me just write prime field, or there are no such, then it's transcendental. So it basically says that Fa at 0 on all prime field F. What can you say about an element? Yes, that's basically it, without quantifiers. Either there is some polynomial over a prime field with branches on it, and then all other formulas you can say are somehow implied by this, or there is no such, and then you have to say all of these inequalities. Okay, so now fact or remark. Which will be used, but I should skip some things. So in extensions, by the last fact, which I erased, but if this is substructure and then quantifier-free type computed in M is the same as quantifier-free type computed in N. That was exactly this fact. They have the same quantifier-free formulas. M. And for example, type computed in R of -1 is not. Because here you have, it has a square root here and it doesn't have a square root here. So you have this sentence which distinguishes okay, so now fact 2 so there will be criterion. Okay, I want to express equality of types or quantifier-free types using isomorphisms. And this will help me to show quantifier elimination for ACF. So let me say that I have two tuples. Okay, I will not write these bars anymore. And those are L structures. So I want to understand when types are equal. So when two elements cannot be distinguished. let's say first in terms of quantifier-free formulas. So this is something like group, okay, like a local group table. If and only if there are L substructures M0 in M and 0 in N, which are such that M0 is isomorphic with N0 in the way, okay, such that many things happens. M0 contains A, N0 contains B, M0 is isomorphic with N0 in the way taking A to B. So I don't know, picture maybe. And some tuple. So there are several elements. Here we can find which are isomorphic, and this goes to this. Okay, so somehow two elements have the same quantifier-free type, if and only if in a way they are locally isomorphic around this A and B, in a sense.
Like in field theory.
Which theory?
In two elements have the same roots of same reducible.
Yes, you can think. Yes, good. So here, if they have the same minimal polynomial over this prime field, here and here, then you can move it, and if they are both transcendental, you can also move it. So that's the kind of situation in fields. And in general, okay, for complete types, it would be something like this, but not for all models, which I don't want to get into. So there will be only one direction. Okay, so it's like local isomorphism, and now I want global. And global isomorphism implies equality of complete types. Which moves A to B, then the full types, complete types, are the same. It doesn't have to happen the other way. It's kind of homogeneity. Okay, not all, but for the algebraically closed fields, it will also happen the other way. So,
in type P.
B. Yes, thanks. Okay, so the second part, this is the statement we had last time, that isomorphisms preserves the truth. And it's exactly that. That whatever is true in M about A, if you apply isomorphism to it, is true in N about B, if isomorphic preserves to B. So I'm not giving the proof, I'm giving some argument. And here, one direction is also isomorphism preserves the truth, and the other, so M0 is a substructure of M. It makes sense to say it generated by A and the same. So these are kind of like very quick arguments or proofs why is it true. Okay, if it's generated by A, generated by B, if you think how it is generated, you apply all of these actually function symbols, And then, so you start associating A to B, then you have some function symbol which moves A to FA, and it also moves B to FB. So you have to move FA to FB. And you continue like this. And because quantifier free types are the same, then it works. This is a quick idea that it's true. Okay, so that's all I will say about the proof. Yes, so second is obvious. First, one has to work a bit, and still this will be some, at the end, induction of complexity of, okay, actually, what does it mean to be substructure generated? So we have to apply all possible function symbols to elements to this A and to constant symbols, and keep doing this. Like you generate a subgroup. Yes, you apply multiplication to elements of something, and you keep going, and you take neutral element, and at some point it stops. So similarly here. And now there is this main criterion. Shall I? Okay, so maybe if I have time at the end, I will say something about its proof. So it says that the following are equivalent. Theory has quantifier elimination. Two, kind of that always this equality implies this equality. So for all models of T, for all, so now M will be equal to N greater than 0, and for all A, B, in Mn, we have that if we have equality of quantifier free types, then it implies equality of complete types. Yes, so if it's true that for any quantifier free formula, the formula holds on A in M if and only if it holds on B in M, then the same must be true for all formulas at all. This is this implication. Okay. So if you have quantifier elimination, then of course it is true, because you can always find for any formula some quantifier free one equivalent to it. But the point is it also goes the other way. So it has a funny argument in 2 steps, kind of looking a bit geometric, but I'm okay. So let's see how far I get. So let me say proof maybe later. But using this and using fact 2, I can now show the main theorem that ACF has quantifier elimination. Okay, so if you have in your mind all of this, this becomes a statement about extending partial partial automorphisms to global automorphisms. And actually in ACF it holds. So we will check this criterion. We will check this. So take algebraically closed field and two n tuples such that quantifier free type of A in K equals quantifier free type in K of B. So then by this fact 2 we find inside, so we have B. Okay, they definitely intersect, at least on prime field. So by fact, now this M and N are the same. So by fact 2, 1, there are substructures, so subfields, okay, or even subrings, but it doesn't matter. Okay. Let me say already subfields.
What is K, A, and K?
Yeah, so this is picture to something I didn't write yet. There are subfields. I may be cheating here, there are subrings, but they are domains, so it will extend also to the ring of fractions, subfields.
And now M and N are same and it's K, right?
Yes. So this is a tuple, so I'm writing like this. And then maybe I wrote not like this. Okay. And which moves A to B. So I'm completing my picture now. There is this thing. So let's see. Well, so now I'm cheating again. That will be a problem for you. That any such partial, so this is like partial automorphism, extend to global automorphism if K is algebraically closed. So since K is algebraically closed, extends to
In fact 2,
Uh-huh.
you take a tuple from the MN. I would like to ask that you take structures MN as structures. I want to ask that their universe are MN and N.
No, M, okay, so this is wrong. I should have said was that the issue?
So the universes are M0 n?
M0, N0. Like here.
But
So this A is like A1 to AN. This
yes,
B is like B1 to...
M0 is substructure or on
Yes, substructure.
A is element of universe of M0.
So A is a tuple of elements. Yes, A is like A1 to AN, and each of them is from M0.
But you are taking an isomorphism and
Yes.
you are taking A to B. I mean,
So by this I mean, of course, that
yes, I get it, but
A1 goes to B1, A2 to B2, AN to BN.
you have two structures M0 and N0, and their universes are M0 and N0 respectively.
Yes.
And then you are saying that I'm gonna construct a isomorphism that takes A to B.
But yes, but it's not fully formally correct, by which I mean it takes A1 to B1, so this is the meaning of this, that it takes A to B. So formally it doesn't psi takes A to B, but it's nth Cartesian power if you want.
So isomorphism is from
M0 to N0.
okay.
Okay. You can always, okay, if I see what you mean, but I didn't define such a thing, no. If you want to treat it as one element, this should be an element of the power, but I didn't put any structure on the power, so no. No, I like this. It was just a short way of saying each tuple goes to corresponding, each coordinate goes to corresponding coordinate. Yeah. Yeah, so I was a bit quick here. Yes, so here the theorem is if we have any isomorphism between two subfields of algebraically closed fields, it extends to automorphism of the whole field. Quite similarly like before in this proof of which one? This one which was used in Hilbert, Nullstellr and Zatz. Then we had extensions to big algebraically closed fields, and then there was isomorphism between them. And this is something like a bit stronger, kind of, because it gives a stronger result. That inside you can find this isomorphism here. Okay, so either you or we together will prove it on Monday. But then, of course, and then by fact 2, since again I'm writing in short like this, there are or A1, AN, B1, BN, everything goes to each other. We have that type so by this criterion okay. Yes, so this was maybe too quick. And now I have okay. So I have 2 pages of other stories, so let me continue with other stories, and probably there will be no time for this proof. So corollary of this quantifier elimination is that if K is algebraically closed, that all definable subsets of K are of simplest possible form, finite or cofinite. Definable subset of K, just the first power, okay, so this was noticed for quantifier 3. This was problem 16, that it is true if we look at quantifier. Maybe 17. And these theories, such that such a thing happen, also have a name. So in this hierarchy of Shelah, of more and more complicated theories, those are like the simplest, although it has named simple theory for something else, but which is not that simple. Theory T such that for each model of T definable subsets of M are finite or cofinite is called strongly minimal. So, for example, this case here is strongly minimal. In terms of Morley rank, it would be Morley rank 1 and also Morley degree 1, like the smallest from dimension point of view. Okay. So I have for the end some examples without proofs of other theories, which are, okay, some of them are even strongly minimal, but which have quantifier elimination. This. DLO, this is dense linear orders without endpoints. This is theory in the language of order. Yes, like cases here, order should be dense. Between only 2 points we can find another, and there is no minimum, no global maximum. It has quantifier elimination.
Actually, this proof of it is much easier.
Yeah, now actually which criterion can this be used? So here actually I use something like each algebraically closed field is homogeneous to be able, so I didn't have to go to some extension, which would be also possible, but require more notions.
This is also by homogeneity.
Okay, so it might be the same.
This is something, I can't completely...
So here actually, okay, the thing is that here it's relational language, so this M0 will be exactly a tuple, because if you have only relation, the structure you generate is the set.
Yes.
You just restrict your relation to set. Okay, so then, yeah, I get that there is not much to do indeed. You have two finite sets. It's obvious, okay, they are ordered, so it's obvious how the automorphism can go. And you can extend, I believe, just putting.
Yes. Everything in between can fit.
In between can fit, and outside can be squeezed a little or stretched.
Yes.
But in between can be. Because in between is always infinite, okay. So it also can be stretched or extended, yeah. Because the problem would be in between would be different number of elements, but of course not, because it's dense. So yes, the same can you see? I don't plan to show it.
Sorry, I'm sorry for interrupting.
Yeah, but okay, still I have to be stuck with some time and no more time to prove it. So it's very weird. Yeah. So here we have some A1, A2, maybe just A3, B1, B2, B3. Okay, maybe it's not the best way to write it. There is like one here, like one here. But, okay, now I'm not so sure. It's okay in Q, but I'm afraid in arbitrary structure it may happen.
But they have...
So actually they're maybe not homogeneous. Because it may happen that here it's like Aleph 0 and here Aleph 1.
Yeah, but I mean, of course, but...
So let me note. So I think that actually shows that they are non-homogeneous models of dense linear order.
But of cardinality Aleph 0,
Cardinality Aleph 0, but in this criterion I'm taking all possible. Okay, if you show that theory is complete, then probably, so let me know that. So the idea was that we have isomorphism, this partial one here, and then we extend it to the whole thing, just finding bijection here, 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 and here, and it is possible in Q, because all those parts are countable.
Yes.
But I can imagine other dense linear orders that sometimes there will be something dense like here countable, but here will be uncountable.
I can look at it.
Okay, so the problem the problem could be that we could have a model of dense linear orders. I guess, yeah, I guess, I'm not so sure, that sometimes interval is countable, but sometimes interval is uncountable.
Yes, this was Alice's question. For it's not LF1 categorical, but LF0 categorical.
Is it possible?
I think so.
In one of the summer schools, I remember.
For instance.
Yes, of course we can. I mean, take intersection of.
Yeah, I guess we can also put like
Q something.
Q and after Q you can put I.
Yes.
So what's a good notation? Maybe like that. Like imagine, put next to each other, kind of. Dense. But then, depending where you are, there may be countable intervals or uncountable intervals. So it's. But it's still okay, it has quantifier relation because in this fact too, it wasn't even only if. It's enough to find some elementary extension so that it can be. But anyway, I didn't want to get into this. Okay, so.
Sorry.
I think that's good. So I think, okay, but I didn't prepare this back, but I think that is exact argument, scheme of argument as for ACF would not work here, but also something easy would work. There are many criteria for quantifier elimination. And I gave the one, okay, I gave the path, which is good for ACF, but maybe not good for other theories. Theory of vector spaces over the field, but not all. I define this language. We have unary function symbols for scalar multiplication for each element of K. Theory of infinite. They are also complete vector spaces. And here it should work if we have local isomorphism between two vector subspaces, it extends to global one by extending the basis, which is actually similar to here. But basis should be something else. Okay, I left as a still it may be a problem. So maybe this was 17, since here I wrote 18. Something negative, the LR theory of reals of R, reals, but in the language of rings, does not have quantifier elimination. Yeah, which is just putting actually several things I said before, how quantifier-free things should look like, and something here doesn't look like this. But there is natural language in which this theory has quantifier elimination. So, okay, all R, I think I defined it, this is ordered rings. So we put also order into the language. So actually I should attribute it. This is theorem of Tarski. maybe this one as well that I see, but I think this is something really first. But if you add order, okay, so the language that we write to make sure, and the order, which is definable, but not in a quantifiable free way. But if you add it, this obstacle, then it has quantifiable notation. So actually, this is another type of interesting theories of fields with order. So in this R, it's actually a complete theory of so-called real closed fields, like algebraic closed. Okay, and axioms. Actually, it's axiomatizing the reals in this language. The axioms are like this. So now I'm describing the theory. Okay? Axioms of fields. Okay, axioms of ordered fields. So addition reserves the order. Now I'm writing smaller equal to which will matter at 1 or at 2. Then sorry. This is a total order, of course. So to every elements are comparable. Multiplication by positive numbers also preserves the order. And even in the axioms, we can say that order is definable by the same formula as before. But the most important one, which really corresponds to this closed, so far I think there are axioms of real fields. And real closed means that every polynomial of odd degree has a solution, like in reals, because from minus to plus.
Until the fourth, it's basically the until fourth one, it's basically the ordered field, right?
Ordered. Okay, 1 to 3 is ordered fields. 4 is this order comes from this. Okay, because how is it? So always if so z times z should be always positive, I think. But maybe it's not the full. Okay, for example, as we may maybe see, talking about rings, this is not true for z, for order on integer. And it's still z is an ordered ring.
No, I said until 4. I mean, it's true.
Until, without 4.
Without 4.
Sorry, without 4. Okay. Yeah, so okay. With 3 it's for ordered fields, with 4 for real fields, I think. Okay, because that also is 4, you see that order really kind of doesn't matter. It can be defined by this. Okay, and for 5 for closed as well. Okay, so I still get last comments. Okay, and then I will stop. And those kind of fields have interesting structural theory. Which is all minimality. So here, still quantifier elimination implies that finable subsets are finite unions of intervals, maybe degenerated. So by point is also interval from A to A, maybe infinite. Okay, and such theories can be formalized are called O-minimal. Like so strongly, okay, so in strongly minimal, these base sets are just finite sets. Here there are intervals, so more complicated. O stands for order. So last thing I want to say is this old amazing theorem by Rilke, which gives some impact to this theory that was a long time open question. And also in that exponential function, it is still a minimal.
When is this thing? Did you check?
Huh?
When is this result? One was
90s, 90s.
90 years.
Okay, so now it's over. Thank you.